My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I'll be discussing interrupt controllers. In particular, I'll introduce the old and new mechanisms for delivering interrupts from hardware devices to the CPU. These methods include the original programmable interrupt controllers and the new advanced programmable interrupt controller with message-signaled interrupts. Interrupt controllers provide an interface for hardware to signal the CPU whenever a device needs attention. It's important to note that this signal only includes a message that essentially says, "Hey, I'm a device, I need attention." The CPU historically then actually does have to go and poll the device to get any data that the device may have. The older mechanism for performing this operation was called a programmable interrupt controller, or PIC, and it actually required dedicated lines to be added to the motherboard. The ISA, or Industry Standard Architecture bus, which dates back all the way to the first PC back in 1987, and older versions of the PCI, or Peripheral Component Interconnect bus, utilized this mechanism. The new mechanism, or the Advanced Programmable Interrupt Controller, is used on PCI Express devices and some newer PCI devices. Now, the old controller, or the Programmable Interrupt Controller, actually consisted of two Programmable Interrupt Controller chips that were attached to each other, with one of the chips being attached to the CPU. The so-called master chip was the one attached to the CPU, and pin 2 of that master chip was attached to a slave chip. Each pin on each of the two chips allows for 16 interrupt numbers to be created. Interrupts 0 through 7 correspond to the pins of the master chip, and interrupts 8 through 15 correspond to the pins of the slave chip. Now, it should be noted that since pin 2 of the master chip handles the slave chip, that the master programmable interrupt controller only supports an effective 7 interrupts. So there are only 15 usable interrupt hardware lines for devices. And these are numbered 0 through 15, but we have to skip the number 2. Now, historically, pin number 0, which corresponds in software terms to what we call interrupt request line, or IRQ0, was connected to the timer. Interrupt request line 1 was connected to the keyboard. Different ISA and PCI devices could then use the remainder of the master chip by connecting to IRQ lines 3 through 7. On the slave chip, pin 0, which corresponds to IRQ 8, was connected to the real-time clock. Pin 4, corresponding to IRQ 12, was connected to a PS2 mouse. Pin 5, or IRQ 13, connected to the math coprocessor, which was a separate component from the main CPU in earlier PCs. And then pins 6 and 7, corresponding to IRQ lines 14 and 15, connected to the IDE controllers. These were used for disk and eventually for optical devices. This left pins 1 through 3 on the slave controller, or IRQs 9 through 11, available for hardware devices. Now, these interrupt lines on the motherboard were actually circuit traces. These were conductive paths etched into the motherboard that allowed interrupts to be received from devices. There were 15 lines available of the 16 that could be used by devices, with lines 0 and 1 reserved for the timer and a PS2 keyboard, respectively. Actually, even before the PS2 reservation, the original AT keyboard. ISA and PCI add-in devices actually had to share interrupt request lines, and this sharing could lead to hardware conflicts that could lock up the system. It was thus up to the system owner to manage the sharing by setting little jumpers on the add-in cards so that the cards were using different IRQ lines. There were also performance issues when IRQ lines were shared, because the operating system actually had to poll each device sharing an IRQ to determine which device it was that raised the interrupt. Polling was still necessary in order to receive any kind of data from the device, regardless of whether it was sharing an interrupt line or not. On modern systems, a completely different interrupt mechanism is used, and this mechanism has a set of memory registers on what's called an advanced programmable interrupt controller. And this set of memory registers is connected to a single shared bus that each device on the system can use to raise an interrupt message by writing that message into one of the memory registers. These are called message signaled interrupts using the MSI and MSIX specifications. And essentially, each device, here I have a timer, RTC, USB host controller, SATA controller, is attached to the bus and indicates its interest in raising an interrupt to the APIC by sending a message over that bus. Now, this message does not contain any data. It's only a request for attention. If the CPU has to be involved in the operation of sending or receiving information, then the CPU actually has to contact the device, in other words, poll it directly. There is a way around this called direct memory access, or DMA transfers, which are used extensively on PCI Express devices. The register on the APIC stores the request for attention until such time as the operating system handles the interrupt request, and then that message is cleared from the APIC. This is the only interrupt mechanism that's available on PCI Express buses. There are no hardware interrupt lines. However, a number of motherboards still have interrupt lines, physical interrupt lines, and have physical PIC pins so that they can support legacy devices. There are a number of specialty legacy devices still in use that need to be supported. Message signaled interrupts do solve a number of problems with interrupt request sharing. The original specification allows each device to use any one of 32 IRQ lines. The MSIX specification will allow each device to use up to 2048 virtual lines, virtual interrupt request buffers, essentially. And this allows for less contention and reduces the need to share interrupt request numbers by device, thus reduces the amount of time necessary for the CPU to determine which device wanted attention. So, main thing to take away from this is that the interrupt controller and the interrupt request mechanism only allows a device to raise a signal that says it wants attention. It's up to the CPU, or on certain buses, up to the device and the memory controller to get the information out of that device and into memory.